Gravitation draws all objects toward the Earth's center. As long as the Earth has existed, objects on the Earth have been acted upon by gravity. But laws that govern freely falling bodies, suspended bodies like this pendulum, or other bodies in motion, were not discovered until the latter part of the 17th century. Galileo, often called the father of modern science, is given credit for helping to develop these laws of motion. According to legend, the Leaning Tower of Pisa was used by Galileo. Supposedly, he dropped objects from the top of the tower and observed how fast they fell. Regardless of whether Galileo made these experiments, we do know that he did research in the physical sciences. Here in this modern physical science laboratory, we will recreate some of his experiments. For example, he dropped objects of different weights and sizes and compared their rates of fall. We will make the same kind of comparison by using slow motion photography. Based on such observations, Galileo concluded that all objects fall at the same rate of speed or acceleration, regardless of size or weight. Objects that weigh very little, such as this feather, seem to be exceptions. But Galileo believed that any differences in acceleration were the result of air resistance. Today, we can prove that Galileo was right by using a glass tube from which the air has been removed. In the vacuum that results, the feather and a coin fall with identical acceleration. Here is the action repeated in slow motion. Another problem challenged Galileo. He wanted to describe the speed of a falling body at any instant. Freely falling bodies move so fast they are difficult to observe, so Galileo devised an inclined plane, much like this one, to reduce or dilute the speed of fall. Galileo used a water clock to time his experiments. Here, a modern electric timer is used to click off the seconds as the object falls. And this device releases the object, such as the steel ball, and simultaneously starts the timer. The distance the ball rolls in each succeeding second varies depending upon the elevation of the plane. Now we will see the action in slow motion. After 1 second, the ball has traveled 10 centimeters. In 2 seconds, 40 centimeters. In 3 seconds, 90 centimeters. In 4 seconds, 160 centimeters, and so on. Here are the experimental results. Using similar facts, Galileo noticed that a relationship existed between the distance traveled and the time squared. Using our experiment as an example, at the end of 1 second, the ball has moved 10 centimeters. At the end of 2 seconds, it has rolled 10 centimeters times 4, or 10 times 2 seconds squared. At the end of 3 seconds, the distance is 10 times 3 seconds squared. And at the end of 4 seconds, 10 times 4 seconds squared. As a formula, s, the distance, equals 10 times the number of seconds squared. Expressed in terms of acceleration, s equals 1/2 the acceleration times the seconds squared. This formula applies to all objects in motion, such as the ball moving down the inclined plane. For the special case where an object is falling freely instead of rolling, The formula S equals 1/2 AT squared becomes S equals 1/2 GT squared, where G is the acceleration due to the full force of gravity. Although the Tower of Pisa experiment, so often associated with Galileo, may never have actually taken place, there is no doubt that Galileo deserves an honored place in the history of physical science. He was a pioneer in experimental work, and he developed formulae to represent some of the basic laws of motion.